you're going to be taking your Chapter 6 test on Thursday. That's right before that 4-day break that you have, right before the ACT you come back and take. And just kind of to give you a quick reminder here, the Chapter 6 test includes solving triangles from before spring break, so law of sines, law of cosines. It includes the vector sections, which you're probably well practiced with now that we've come back from break. And then it's going to include this trig form of a complex number. So there's kind of like 3 separate topics that are covered on the Chapter 6 test. So just kind of be aware of that. You're going to see some connections to trig form of a complex number related to our vector work and also related to some of the things that we did back in Chapter 4. So these things just kind of keep coming back to us. So first we're going to talk about complex numbers. And you guys talked about complex numbers. You first learned them in Algebra 2. Does anybody remember, like, what's special about complex numbers? That's where we bring in the I, right? So the standard form for a complex number is A plus BI. That should look familiar to you. We worked with complex numbers in semester 1. Sometimes we had complex number solutions. Okay? And I always stress, like, when you write a complex number, it should be A plus BI so that the imaginary part is second. So in this standard form, Z is just the common letter that we use to represent a complex number. A is the real part of the complex number. B is the coefficient to the imaginary part of the complex number. Complex numbers house all the numbers that we work with. So even real numbers are complex, like the number 5 is really 5 plus 0i. We just don't teach that to you in the beginning. We just call it 5. Now, to graph a complex number, you cannot graph a complex number on the real coordinate plane with the x and the y axis because there's no place for imaginary parts. So we graph on something called the complex plane, which we'll draw to look like our regular Cartesian coordinate plane. Okay. But in the complex plane, the horizontal axis is the real part. So you can think horizontal is where you move left and right A. If A is positive, go right. If A is negative, go left. And then the vertical axis is the imaginary axis, so that's where you move for B, up or down, depending on whether B is positive or negative. So this is like your B. So you can think about a complex number. Okay? If I were going to plot it, I would start at the origin 0, 0, and whatever A is, I'll move A units right or left, and then whatever B is, B units up or down. So you can almost think about it like an ordered pair, A comma B, but it's representing A plus BI. Now, tell me about what you know about absolute values of just regular numbers before we get into complex numbers. What's true about absolute value? Hugh? It's always positive. Why is absolute value always positive? Because it represents the distance from 0. So if we're doing absolute value of a complex number, it still represents the distance from 0, but in this case, we're talking about 0, 0, so it's the distance from the origin, 0, 0. And what Hugh said in the very beginning, that it's always positive, that will still remain true because it still represents a distance, and distance is always positive. So if we were looking at this point that I plotted here, AB, and we wanted to find its distance to 0 right there, what would you guys use to find its distance? Somebody besides you. How could you calculate distance, Maggie?
Square root of a squared plus b squared.
Pythagorean theorem, right? Square root of a squared plus b squared. So the absolute value of a complex number z is equal to the square root of a squared plus b squared. Excellent. You could imagine here drawing the right triangle. A, B. And so you're finding the hypotenuse of the right triangle. So this square root of a squared plus b squared, this idea of using the Pythagorean theorem for a right triangle, it just keeps coming back, right? We keep seeing the same picture over and over again. So be thinking about that as we go through our notes today. Now, one thing to note about the absolute value there, when you plug in for b, you are only using the coefficient, not the I. So never plug I into this absolute value formula. If you were to plug in I and then square it, you would get I squared, which we know is -1, and it really shouldn't be negative underneath that square root. They should both be positive. So only the coefficient for b. I'm going to give you an example to try on your own. Okay, so it's going to be, I'm going to give you the standard form, and I'm going to ask you to graph it. I'm going to ask you to find the absolute value. So plot z equals 3 minus 4i, and then also find its absolute value. Okay, so I'm walking around, I'm seeing really good work. You're just plotting a point here. This is different than a vector, so you don't need to draw the arrow there or the line. So you're just plotting the point, 3 minus 4i, and then you're going to calculate, it should be in the fourth quadrant. Then you're going to calculate its absolute value. So the absolute value of 3 minus 4i is the square root of 3 squared plus -4 squared. Notice I'm not including the I. So you're going to get the square root of 9 plus 16. Square root of 25 is 5. Of course, not always will it come out to a perfect square. So if it's not a perfect square underneath the radical, go ahead and simplify that radical. And then you're done. Any questions about graphing or absolute value for complex numbers? Okay, excellent. So now we're going to separate from that old complex number that we knew back in Algebra 2 and we used for semester, and we're going to start talking about the trigonometric form of the absolute value. So that old form, standard form, a plus bi, is sometimes referred to as the rectangular form of a complex number. After chapter 6, we're going to do a chapter 10 on conic sections, and we're going to follow that up with a second chapter 10 on parametric and polar stuff. And so we're going to see these phrases, rectangular and trigonometric, again with polar. So the thing to remember about rectangular form is it has A and B in it, where A represents left and right direction on my coordinate plane or my complex plane. B represents vertical direction up and down on my complex plane. And when you're like plotting those points, you're always kind of like following the path along the sides of a rectangle, right? You turn at 90 degrees and change your direction. Okay, so that's kind of why it's called rectangular form. Trigonometric form is different in that it has r and theta. So it's not going to say left, right, up, down. It's going to say what direction angle you want to move in and then how far you want to move along that angle. So it's kind of like from component form to component form with magnitude and direction. In component form, b sub 1, b sub 2, you just go right, left, up, down. In component form, you know the magnitude of the vector, so the length of the vector, and the direction of the angle is. So I've got that same image we keep seeing over and over again. I've got a point plotted there in the first quadrant. We're going to call it AB. It's representing A plus BI. I've labeled my R, which in vectors we would call the magnitude. Back in chapter 4, we did use R for like radius of a circle. It has a new name. It's called the modulus. Someone asked me second hour why they use the word modulus in argument. I don't really know. So I wrote it down and I tried Googling it and I haven't found anything. So I'll ask some other teachers to see if they know why these two words. But in trig form, we're going to call it modulus. Okay. And then the angle between the positive x-axis and wherever that point is, it's going to be between 0 and 360. That's your theta. And I'm going to make a little note there. Your argument should be between 0 and 360. I'm saying include 0, but not 360. Goes back to chapter 4. 0 and 360 are the same angle. Let's choose the smaller one. Okay. So to write it in trig form, we're obviously going to be using trig stuff, right? So think about all the things trig with that picture and tell me what things you know. Q, what's one thing you know? R cosine theta is equal to A. And how do you know that? It's like the vector work that we did, right? The horizontal component. If you imagine a right triangle right here with side lengths A and B, the cosine of theta is A over R. So to solve for A, you would multiply both sides by R. So the horizontal component, or the horizontal side length here, is R cosine theta. What else do you know? Trig-wise. R sine theta equals B. And again, how do you know that? The sine of theta is equal to B over R, opposite over hypotenuse. Multiply both sides by R, and then you have B all by itself. So we just found out A and B. In rectangular form, we have A plus BI. We can simply substitute. So instead of writing A, we'll write R cosine theta plus B times I, but B is really R sine theta. Now, it does not matter if you write it R sine theta times I. I just write it I times R sine theta. So either way would be same. That's trigonometric form. Star, circle, highlight, box, whatever you want to do right there. And I like Q's connection. It's really the horizontal and vertical components from vectors, right? Of course, we're not talking magnitude, we're talking R or modulus, and we're not calling it the direction angle, we're calling it the argument. That's really the same idea. Okay. The only difference mainly is we've got the imaginary part, and we're writing it in standard or in complex number form. What do both of those terms have in common? R. So you can also write this, if you factor out R, you could write it as cosine theta plus I times sine theta. Okay, so that's another way to write it. You can factor out the modulus. And then, you know, mathematicians, we can get a little bit lazy, or we want to make things a little bit easier sometimes, so we make up abbreviations, right? So we have an abbreviation for this. R kiss theta. I'm saying kiss because C is for cosine, so it's the heart. Cosine plus I sine theta. That's what kiss is. Note to yourself, kiss is not a new trig function. Okay, there are only 6 trig functions. Okay. I like to use this notation because I don't like to write as much, right? If you're really comfortable and you don't mind writing out the whole thing, that's fine. If you're comfortable with the abbreviation, also cool with me. So when you see R kiss theta, it means R times cosine theta plus I times R sine theta. Means the same thing. Okay, now before I leave this slide, we have A and B in terms of R's and thetas. Can you write R and theta in terms of A's and B's? What would R be equal to? A squared plus B squared equals R? The square root of A squared plus B squared. Okay, so I'm going to make a little note here. R equals the square root of A squared plus B squared. It's just like the magnitude, okay, or our radius in chapter 4. So we're using the same formula there, Pythagorean theorem. And what could you say about theta, should you ever want to find theta? Inverse tangent of B over A. Excellent. So each time I draw this picture, there's 4 equations we can write. There's the Pythagorean theorem, R squared equals A squared plus B squared, which gives us R equals square root A squared plus B squared. We can write one equation for tangent, tangent theta equals B over A, inverse both sides, and we have theta. We can write one for cosine, cosine theta equals A over R, multiply both sides by R, and we have A. And we can write one for sine. So we're doing the 3 trig ratios and the Pythagorean theorem for that right triangle every time, right? Let's put this to use. Let's write 6 minus 6i in trigonometric form. Okay, so 6 minus 6i is currently in what form? Rectangular, which looks like A plus BI. So when it says take something in rectangular form with A's and B's and put it into trig form, what do we want in our answer? Instead of A's and B's, we want R's and thetas. So have a quick chat with the people around you. Are you able to find R and theta for this complex number? What would you do? How are you guys going to find R? Pythagorean theorem, square root of A squared plus B squared. A is 6, B is negative 6. How are you going to find theta? Inverse tangent, negative 6 over 6. And make sure your angle is between 0 and 360. Calculate those, check in with the people around you, see if you agree. I do my work and I get to r equals square root 72, theta equals negative 45. What will you tell me to do to my modulus and my argument? Add 360 to my argument. Does that get me in the right quadrant for 6 minus 6i? Yeah, because I would go right 6, down 6, so I'd be in the fourth quadrant. So I'm going to add 360. You should always give me a positive angle between 0 and 360, so that's 315. Will you tell me to do anything to my modulus? Simplify the square root, right? Always put it in simplest radical form if possible. So this is really 36 times 2, which would be 6 square root 2. So now that you have r and theta, you just put it into the trigonometric form. I like to use my shortcut version. So I'm going to plug those in to r kiss theta. So I'm going to say 6 square root 2 kiss 315. That is an acceptable answer. If you prefer to have it written so like you remember what kiss is, okay, you could also write that out as 6 square root 2 cosine 315 plus, I'm going to say 6i square root 2 sine 315. Or I times 6 square root 2 sine 315. You put it in different orders because you're multiplying it all together. Did you simplify that like do I simplify it by evaluating sine and cosine? No, because if I simplify it with sine and cosine, then I won't be in trig form because I won't see the trig functions anymore. I'll be putting it back into 6 minus 6i. So it's kind of like that whole piece of, I think it was like number 9 on your quiz review and your quiz yesterday. In trig form, we want to see cosine, we want to see sine. Okay, so looks kind of terrible, but really not so bad, right? Can you go the other direction? If I give you trig form, can you guys tell me rectangular form? So I'm giving you a complex number z. Z is equal to 8 kiss 2 pi over 3. And we want to write it in trig form. So we want to write it in standard form or rectangular form. Right now, it's in trig form. So I know that 8 is my modulus and 2 pi over 3 is my argument. What do I want for standard or rectangular form? I want A and B. So kind of frame in your mind, if you're asking to switch forms, what's the big change there? You've got to change modulus and argument, r's and thetas to a's and b's. So again, talk with people around you. How are you going to change it back to A and B? Did you guys come up with a plan? Okay, our complaint did it, our plan did it. Do you guys have a plan? Yes. I'm just gonna do it. Oh, very good. Plan over here. Can you give me an exact value? if the angle, the argument is on your unit circle, give me an exact value. It's always good to practice our unit circle knowledge. Which one? And then make sure that you simplify that. Okay, I see a lot of people, a lot of groups said, well, let's just plug it back into the A equals and the B equals, right? So it's kind of like what Paige had asked about on that last example. Should I actually work it out? Should I do the cosine and the sine? When you do, you go back to rectangular form. So for 2 pi over 3, remember on the unit circle, its coordinates are -1/2 square root 3 over 2. And then this is your cosine and this is your sine. So you can sub those in. A is equal to 8 times -1/2. B is equal to 8 times square root 3 over 2. And you're going to get -4 and 4 square root 3. So then you can plug into A plus BI. That's just -4 plus, I'm going to write mine as 4i square root 3. If you wrote I times 4 square root 3 or 4 square root 3 times I, that's all the same thing. Multiplication is commutative. Okay. Any questions about going from trig to rectangular form? You'll have to be real careful, make sure you know the values on the unit circle. Common mistakes for people are signs, positive and negative, and then of course the 30 and the 60-degree angles, getting those two mixed up. So you might need to review your unit circle. Okay. All right, we've got one other thing to talk about today, and that's being able to multiply and divide complex numbers in their trig form. Okay. So they each come with a formula. Here's your product formula. So we're doing the product and the quotient of complex numbers. I'll give you an opportunity to just jot that down. Remember, the z's on the left just mean complex number. Now, you know how to multiply complex numbers in rectangular form. If I gave you 2 plus 3i times 1 plus 4i, you basically distribute, FOIL it all out, I squared equals -1, combine like terms, and then get another rectangular form. Okay. If your two complex numbers, z sub 1 and z sub 2, are in trigonometric form, then you can multiply the modulus for each complex number, so r sub 1, r sub 2, whatever the modulus is, and then kiss the sum of the arguments. Now, what do you think the division formula looks like? Z sub 1 divided by z sub 2. What are you going to do with the modulus? If you're dividing the complex numbers. Divide them, and what are you going to do with the arguments? subtract them. So there's another formula. Z sub 1 divided by Z sub 2 equals R sub 1 divided by R sub 2 kiss theta sub 1 minus theta sub 2. And back in rectangular form, in order to divide complex numbers, we had to multiply by that conjugate of the denominator, just because we weren't allowed to leave the i's in the denominator. So I think you're going to find out, if they're already in trig form, this is actually probably a lot easier than multiplying and dividing in rectangular form. Okay. Multiply or divide your modulus, add or subtract your argument, maybe simplify. So let's look at a couple of quick examples. First one is going to be multiplication. Find the product of 3 kiss 60 times 4 kiss 30. So they're already in trig form. There are some problems on your homework where they're in standard or rectangular form, and it has multiple steps. It asks you to first rewrite them. So you'll have to find r and theta in trig form, and then do the formula for the product. So Z sub 1 is 3 kiss 60, Z sub 2 is 4 kiss 30. Those are just my two complex numbers I'm multiplying. What should I do with the modulus 3 and 4? Multiply them, so 3 times 4. And what should I do with the arguments, 60 and 30? Add them, so 60 plus 30. I'm showing my work here. And then I'm going to simplify, that's 12 kiss 90. If the directions in the textbook say leave your answer in trig form, leave it alone. So this is trig form. If the directions in the textbook say write it in rectangular form, then you got to expand it and evaluate the cosine and the sine of 90. And so I could do 12 cosine 90 plus 12 times I sine 90. That's what KISS expands to, right? What is the cosine of 90 degrees? 0. And the sine of 90 degrees? 1. So then that would really just be 0 plus 12i, so I can write 12i, and this is in standard or rectangular form. So where you go depends on the directions. Most of the time, if it's an angle on the unit circle, keep going. If it's not an angle on the unit circle, just leave it. And then let's do one that is division, just so you can see the division formula at work. We'll kind of shorten the work that we do right here. Find the quotient of 12 kiss 70 and 3 kiss 25. Since they're already in trig form, I can go ahead and use my formula for the quotient of two complex numbers. I'm going to divide my modulus for each, so 12 divided by 3 is 4 kiss. What do I do with those arguments? Subtract, and always subtract numerator minus denominator, so 70 minus 25 is 45. And then that's trig form, right? Because it's an angle on my unit circle, I'll go ahead and keep going. It'll be 4 times the cosine of 45. What is the cosine of 45 degrees? Square root 2 over 2 plus 4i times the sine of 45, also square root 2 over 2. So there I'm not like showing all my work, my expanding of KISS. If you understand it, you might not have to write it all out. And then my 4 over 2's are gonna reduce. And so I have 2 square root 2 plus 2i square root 2. If you've got this 2i square root 2 in a different order, like 2 square root 2 times I, that's fine. And this would be our rectangular form. Any questions? Okay, so not too bad. It's really like not super hard math again, but really understanding what you're actually doing. And when you're reading your directions in your textbook, you're going to have to pay careful attention to if they're saying rectangular or standard form or trig form. So think about, do I want A's and B's or do I want R's and thetas? You do have a textbook assignment for the weekend.